Welcome to the final lecture of week 2 of Math 320. I know that this week has been quite heavy in terms of theory. If you hold out, next week will be more concrete with some exercises you can get your hands on. Let's finish up this week by talking about some properties of the real numbers. Recall that we are taking as an axiom that the real numbers contains the rational numbers and is order complete. First, the least upper bound property also holds for R. Recall that this means if T is a non-empty subset of real numbers which has an upper bound, then there is a least upper bound of the set T. And the least upper bound is a real number x0 that is both an upper bound of T and the smallest such. Note that in practice, when given a set T and a number x0, to verify that x0 is the least upper bound of T requires proving two things. First, you need to prove that x0 is indeed an upper bound of T. This means proving that every element of T is no greater than x0. Second, you need to prove that there cannot be a smaller upper bound. You can either argue directly by showing that any upper bound is at least x0, or you can argue by its contrapositive and show that any z less than x0 cannot be an upper bound of T. This proposition is a direct consequence of the one for general order complete sets that we talked about in lecture 3. We can also rephrase the least upper bound property in terms of the greatest lower bound property. This says that if T is non-empty and bounded below, then it has the greatest lower bound. The definition of the greatest lower bound is exactly what you might expect it to be. The greatest lower bound property, in fact, also holds for any order complete set. We can prove it in general by modifying the proof given in lecture 3 of the least upper bound property. For the real numbers, however, there is a simpler proof taking advantage of the arithmetic properties of the ordering. We can deduce the greatest lower bound property from the least upper bound property by considering S the set of negatives of the elements of T. So, if T contains 3, then S will contain minus 3. If S contains pi, then T will contain minus pi. The arithmetic properties of the ordering tells us that any lower bound of T is an upper bound of S, and vice versa. Since T is bounded below, we know thus S is bounded above. So we can apply the least upper bound property to S to find its least upper bound, which we call Z0. Its negative then is a lower bound of T. And there cannot be any greater lower bound of T, since such a number will become a smaller than Z0 upper bound of S, which we know cannot exist. And the property is proven. This slide actually illustrates something general when talking about real numbers. If you have a general statement concerning the greater than or equal sign on the real numbers, you can always translate it to a general statement concerning the less than or equal sign simply by multiplying everything by -1. This principle allows us to save a lot of work. Finally, as promised at the final lecture of last week, we will prove the Archimedean property of reals. It says that given positive real numbers x and y, there is a natural number n satisfying nx is greater than y. Notice that n is always a natural number. This is the power of the Archimedean property. It says that in some sense, understanding the special cases having to do with natural numbers is often enough for us to understand the real numbers. We will come back to this general philosophy later when we talk about limits. And it is good to be able to reduce things to natural numbers, since they have much simpler structure and are more concrete and easier to understand. Let's talk about the proof. This is again a contradiction proof. Suppose that the conclusion is wrong, that there is in fact no natural number making nx bigger than y. This would mean that for every natural n times x is less than or equal to y. So the set of positive integer multiples of x, which we call S, is bounded above by y. Applying the least upper bound property, we can call z the least upper bound. The number z minus x is strictly smaller than z. Since z is the least upper bound, z minus x cannot be another upper bound. So there is an element of S that is bigger than z minus x. Since elements of S are multiples of x, we call this element mx. Since mx is bigger than z minus x, a bit of arithmetic shows the quantity m plus 1 times x is greater than z. But since m plus 1 is still a natural number, m plus 1 times x is an element of S, which is greater than z, showing that z is not after all an upper bound. This is a contradiction, so the Archimedean property must hold. Alright, that's the end of the lessons for this week. Before you go, here is a quick summary of what we learned. In Lecture 1, we defined the concepts of maximum and minimum. Key idea is that maximum and minimum only refers to elements of the set itself. This is in contrast to what we talked about in Lecture 2, upper and lower bounds. These numbers can belong to some exterior set and can only be spoken of meaningfully when discussing subsets of some larger set. In Lecture 3, we defined the abstract concept of a cut and used it to define order completeness. We proved that all order complete sets have the least upper bound property. In Lecture 4, we showed that Q is not order complete and asserted that R is. In other words, we will take as an axiom that R is order complete and base our understanding of the real numbers upon this assumption. We show that order completeness of R implies the Archimedean property. Okay, see you next week.